It is quite possible to have multiple parts in a simulation that interact with one another. Often this interaction involves contact between these parts. Other times you might have a single part with different regions that contact each other, what we call self-contact. In this tutorial, I'll explain the basics of contact, and we'll show how you can include contact interactions in your simulations. The setup consists of three parts: a plank, a block with a semicircular surface on one side, which I shall refer to as the curved block, and a block with flat surfaces, which I shall refer to as the rectangular block. The curved block is fixed on the bottom, and the plank is fixed at one end, making it a cantilever. A force is applied on the free end of the plank, pushing it downward so that it bends around the curved block. At the same time, the rectangular block holds the top surface of the plank flat, preventing it from arching upwards. The dimensions of the parts are displayed in the figure. The plank is made of aluminum 2024 T3 with a mass density of 2,770 kilograms per meter cubed, a Young's modulus of 73.1 gigapascals, and a Poisson's ratio of 0.33. The rectangular and curved blocks are made of AISI 1005 steel with a mass density of 7,872 kilograms per meter cubed, a Young's modulus of 200 gigapascals, and a Poisson's ratio of 0.29. Abaqus does not check to see if parts are coming in contact unless specifically told to do so. One way to do this is to use the contact pairs method. Here we tell Abaqus which surfaces are likely to come in contact so it can keep track of these. The other is the general contact method, which will be covered in a subsequent tutorial. The contact pairs method requires two steps. First, you create a contact interaction property. Here you can provide information such as the tangential behavior properties, the friction coefficient, the friction formulation, the critical shear stresses, and so on. You can also specify the normal behavior and a number of other mechanical and thermal properties of the contact interaction. After that, you create the surface-to-surface interaction itself. Here you define the actual surfaces that will come in contact, the master-slave relationship between them, and set options such as the discretization method and the sliding formulation. We'll explain all of these terms over the course of the tutorial. We will have contact in two regions. The first is between the plank and the curved block. We will make this interaction frictionless. The second is between the rectangular block and the plank. Here we will specify a friction coefficient of 0.1 and we'll tell Abaqus it is isotropic, meaning that the friction coefficient is the same in all directions. The analysis will be carried out in three steps: the initial step, a make contact step, and an apply force step. Contact is a severely discontinuous nonlinearity. By having a separate step to establish contact, we make work a little easier for the solver and prevent chatter, thereby reducing the number of iterations required to solve the analysis. We will talk more about this in the course of the tutorial. So let's get started.